Hi everyone, my name is Vangelis and I will be presenting our work on large-scale pre-training for grounded video caption generation. Our goal is to address the task of grounded video caption generation, where the input is a raw video and the challenge can be broken down into three subtasks. First, the model must perform captioning, generating a natural language description of what's happening in the video. Second, the model identifies the noun phrases in the caption, essentially the key entities like the man, the ball, the cup, or the jar. Third, the model carries out grounding, which means linking each of those noun phrases back to bounding boxes in the video frames. Our motivation is scaling up learning for robotic manipulation. One way to teach robots is through learning by demonstration. Thanks to platforms like YouTube, we have access to millions of instructional videos where people show how to perform different tasks. But this raises a key question. How can we obtain these videos and label them in a way that makes it easy to identify relevant examples for a specific task, such as pouring a liquid shown on this slide? Our work on grounded video caption generation makes a step in that direction. Our first contribution is an automatic annotation method for grounded video captioning, which consists of three stages. In stage 1, we perform frame-level grounding using a grounding model for still images. In stage 2, we aggregate the frame-level captions into a video-level caption using an LLM. In stage 3, we connect the bounding boxes across frames using an LLM, obtaining consistent bounding box tracks. Using this method, we automatically annotated the how to ground 1 million pre-training dataset. It contains about 1 million videos and around 80 million bounding boxes, making it one of the largest resources available for video grounding. How to ground 1 million is well suited for pre-training, though of course, given its scale and automatic construction, it does contain some level of noise. Beyond the dataset, we also introduce our model, Grove, designed specifically for grounded video caption generation. Here is how it works. Step 1. We take the raw video and feed it into a video encoder which extracts rich spatiotemporal features. These features are passed to a large language model which generates the caption and predicts the location of the noun phrases. Here we use adapters to enhance spatiotemporal modeling. Step 2. We add a decoder that again takes in fine-grained spatiotemporal features and grounds those noun phrases to bounding boxes in the video. This stage also relies on adapters to effectively capture spatiotemporal contexts. Importantly, we also introduce a temporal objectness head, which predicts whether a given object is present in each frame. This makes the grounding more reliable and robust. Finally, we introduce the iGround dataset. Unlike how to ground 1 million, which is large and noisy, iGround is small but highly accurate because it has been manually annotated. It consists about 3,500 video examples split into training, validation and test sets, and thanks to its precision, iGround is particularly well suited for fine-tuning models and for providing a reliable benchmark to evaluate grounded video captioning performance. We evaluated our approach across 5 different datasets, comparing it with the strongest methods available. Across the board, Grove achieved state-of-the-art performance on all 5 benchmarks. This highlights not only the strength of our model architecture, but also the value of combining large-scale pre-training with fine-tuning on small-scale but highly accurate datasets. We also investigated the scaling behavior of our proposed model. What we found is clear. As we increase the size of the pre-training dataset, the performance of the model consistently improves. Across different evaluation metrics, the model achieves the best results when trained on the full how to ground 1 million dataset. This provides strong evidence that large-scale pre-training is crucial for grounded video captioning. Here, I'd like to share some qualitative results of our method. For each input video, we generate a caption describing the activity, and we also overlay the predicted bounding boxes directly onto the video frames. This allows us to see how well the model aligns language with vision, not just describing what happens, but also pointing to the exact objects involved in the action. Thank you very much for your attention.